transformable with logarithms. You know, there are a lot of things that we can do to manipulate logarithms as we look at these two, but one of the things they want us to start doing more is getting used to natural logarithm, because that's definitely something you need a lot when you go to calculus. So this example had said, what we want you to do is describe how to transform this from the parent function of natural logarithm of x, how to do that. And then basically do the graph however you want to do it, but make sure you're able to describe this in terms of a parent function of natural log of x. So we looked at this one and said, well, what I know about using natural log would be I can use the change base formula on this right away and say h of x would equal the natural log of x over the natural log of 1/4. But then I start thinking, wait a minute, natural log of 1/4, really shouldn't leave it like that either, because that's the natural log of 4 to the negative 1. And with powers, we really should be bringing that stuff forward. So we should really make that negative natural log of 4. And you could go even further. No, not with the calculator. Calculator will take care of all of that for you. All right, so this would be, oops, I don't want my two negatives, I just want one. So now they're asking us what would be the transformation. Well, like we talked about yesterday, this is the parent function, so you really want to separate out that negative 1 over the natural log of 4 so that you can talk about that transformation. And now we've got two things going on, because yesterday we just had 1 over, this one was the natural log of 5, and we said, okay, that's going to be a vertical shrink. But hang on a second and think about it for a bit and go, okay, natural log of 4. If I snail shell that, that says e to the something has to be 4. Yeah, that's going to be a positive number. So this is definitely going to be a fraction here. So we definitely will still have a vertical shrink of 1 over the natural log of 4. But what do we do with that negative? The negative in front would be a reflection over the x-axis, because remember, those always come as if they were over here, and we divide through to get those. So this will be reflection over the x-axis, vertical shrink, factor 1 over natural log of 4.
So we just bring the whole 1 over natural log 4?
We do. And some books would have you put that as a decimal instead, but I mean, it's just a matter of punching it in if you want to do the decimal equivalent of that. But it would be perfect answer to just leave it. I'm dropping little slips of guessing paper here. 1 over the natural log of 4. So now, I don't want to graph it that way. That's nasty. Most of us don't think in terms of e and natural log and all of that. So instead, I go back to the old way that I've always graphed logarithms, which is, let's go back to what we had, which was really y equals logarithm base 1/4 of x. And let's just snail shell it and get a graph that way. You know, it's the easiest way to do it. Why do it a hard way if you don't have to? So 1/4 to the y equals x is what we have. And again, what we're going to do is go ahead and basically make the table backwards and put some values in for y. But this time, because it's a 1/4 base, I do want to flip it. You know, I want some nice numbers out of it. So -2, -1, 0, 1 might be good ones to do for that. And so to the -2 power is actually going to be 16, because we'll flip it and then we'll square it. To the -1 power is just going to flip it. Put a 0 in there. Got a 1. Put a 1 in there. Put a 1/4. And that way we don't have any transformations to mess with or any of that. It's just, here it is. So obviously we're not going out to 16, -2, but that tells us that it's going to be pretty flat. So 4, -1, 1, 0, 1/4, 1. And that's probably even a little bit too much of a slope, since I'd have to go up to -16, -2 to get that to happen. Could we graph it with the reflection and the 1 over natural log of 4? We could, but what a pain it would be. You know, it's just not something we generally are going to do in our head when we do that. And then the last thing to do would, of course, be actually punched in a calculator and take a peek at it, you know, see what you get. And we do see that those transformations would fit if we had used the natural log of x as the parent function. It is going to reflect over the x-axis, and it is going to be a vertical shrink that we see with the black little piece there. So check it out, and we know, hey, but we got the right graph. We just didn't necessarily graph using E when we went through it. So now, what we just did in that last one is a common transformation that can be made with natural logarithm or common logarithm. So we generalize that to say if your base is greater than 1, then 1 over b will be greater than 0, less than 1. And you could rewrite this using the properties of logarithms to become negative logarithm base b of x. And it wouldn't be difficult because we'd do this. We'd say logarithm 1 over b of x, right there. Well, what do they really want me to do with this? Because I've got this b to the -1. And it's just like we did with the last graph where we realized we're going to have a negative that we're pulling out in front because that's really b to the -1. So that's a transformation that you can make. Again, I wouldn't graph that way, but we have to know that that's a transformation that can happen. So when given a function like logarithm base 1/4 of x, our base is between 0 and 1, we can immediately rewrite it as negative log base 4 of x. So using the fact that 4 to the -1 is 1/4. Because we can so readily change the base of logarithms with bases between 0 and 1, such logarithms are rarely encountered or used. Don't use bases with fractions very often. It's just something we need to know about. So instead, we try to make sure that our bases are greater than 1, and that's the reason for that transformation, is to make sure that the bases are greater than 1. So, because all of those will behave like natural logarithms, common logarithms, and that way we don't have to learn all the different bases and how they all behave. So this says, logarithm functions, logarithm base b of x would be greater than 1. When your base is greater than 1, when we're talking about e, when we're talking about 10 for common logarithms, all of this analysis that we have here is going to hold. So domain from 0 to infinity, range is all reals, it is continuous, it is definitely increasing on its domain, there's not even or odd symmetry, we're not bounded above or below, there's no extrema, no horizontal asymptotes, we do have the vertical asymptote right here at x equals 0. And the end behavior, because we're just on the right hand side of the y-axis, we're only going to be talking about what's going on that side of the graph. So limit as we approach infinity is infinity. It's going up. So we've got a couple other extra examples here, and they have a little more to them. You know, we've got some transformations and some reflections and all of that good stuff. So sketch the following functions, show the asymptote, the y-intercept, find the domain and range, and determine end behavior. And all we always want to do is get the parent function. And the parent function is just everything without the translations. So what we would want to do is graph negative logarithm base 3 of x. But when we start doing our graphing here, we kind of ignore this negative for a second. We're making our tables. We'll mess with that after the fact, because really what we need is 3 to the y equals x if we snail shell that. And the rest of it we can manipulate in the table. So, once again, it's our y's that are the inputs. I've got a 3 there, so maybe I'll put 1 negative in there. -1, 0, 1, and 2 ought to be good to give me my x's, which would be 1/3, 1, 3, and 9. But now I remember, the shape of this graph also comes along with a reflection. So I think, well, if it was in the front, that was because they divided it from the other side, and that was in front of the y. So if it was in front of the y, this is actually a reflection over the x-axis. but the negative was truly in front of the y. So what I have to do is put a negative in front of all the y's, and that is this vertical column right here. So I need a negative of all of those y's. And I'm not going to use that middle vertical column right there, because this gives me not only my logarithm base 3 of x, but also negative logarithm base 3 of x. That's the shape of my graph. That's my dashed graph. Next. These, I just picked them because they're nice ones.
Where'd you plug it
Oh, 3 to the y equals x, because remember, logarithms are not the way we think. We always translate from exponents. So we quick do a 3 to the y equals x snail shell on that, and then we go from there. So let's graph this dashed. See what it looks like. 1/3 1, 1 0, 3 negative 1, and 9 2. Not too shocking, you know, because we said our logarithm was going to have to reflect over the x-axis, and we did. But we're not done, because we still do have to do translations. I mean, that's the one thing that's easy to do just by counting at this point. So take a look at this up here. How do we need to translate this graph? 1 to the left. So that's going to move our asymptote. Here's our new asymptote. X equals negative 1, since we're moving everything back 1 unit to the left. This is awfully teeny. I hope you can make it out better on yours. Move that 1 unit to the left. There it is. If we put everything else up there for the shape, then all we have to do is some counting to move our graph, which is what we want. That's the easiest way to do it. So where was our new asymptote? Y-intercept. It is at 0, 0, because we were at 1, 0, and we move it back. Now we're at 0, 0. Domain. Negative 1 to infinity, not including that negative 1, because that is an asymptote. Range? All reals. Negative infinity to infinity. Does this have two end behavior statements?
Yes.
Are we going to the left forever?
Oh, no.
Right.
Oh,
So,
I
yeah,
see.
you have to think, are we going to the left forever? Because, yeah, we did cross it, we're going to the left. But we're not going to the left forever. So, we can write the limit as x approaches positive infinity of this graph. And where is it going by the way?
Negative.
Yeah, going down. So we can get that. But it's not going to the left forever. And that's the important part. All right, it looks like we got a little bit more on our plate over here for B, right? Look at that. First of all, way wrong notation here for us. We like that logarithm base B of x minus h plus k. So let's make it look that way by saying we're going to put the logarithm first. And I can't stand that 0.5. I'm going to have to change that to 1/2 right away. But there's something else that's wrong, right? Yeah. So that means we've got a reflection taking place. So. Okay. So with this one, we did everything but the h and k, right? That's what we want to do. We want to do everything but the h and k for the shape. So we really just think of this as logarithm base 1/2 of x equals y to start with. Not a big deal. And we want to put in the y values. What are some good y values for this negatives, yeah, maybe even as far as -3, because -3 would give us 8. And then, yeah, I usually go to 1. I want to see at least 1 on the other side. So our x's 8, 4, 2, 1.
So are you plugging that into half to the power of y equals x?
Exactly. Still snail shelling because logarithm language is like an alien language to us. So we're translating that back into 1/2 to the y equals x. Oh, well, I'm going to need that space later, so I'm going to move that over. But this one had a reflection. Over what?
Y axis.
Because it was in front of the x here. When you reflect over the y-axis, what do you make negative? The x's. So this table actually needs to go out this way so we can get a negative x. Like so. Now the good news is that's the hard part. You know, that's the shape, and then we're just moving it. That's all we're doing. So we're not using this middle column of x's because we needed to have that reflection on there. So we've got -8, -3, -4, -2, -2, -1, -1, 0, and 1/2 1, and that helps us see the current asymptote, which is the y-axis. We know it should do that. It had a negative in front of the x. It's supposed to reflect over the y-axis. So used to be here, now it's over here. Good news. We did that right. So it's just a matter of where do we go with it? Where do we go with this graph?
Well, we have to move it to
Right, 2 up. Going to change your asymptote, isn't it?
Yep.
Exactly. 1, 2, 3. I'll just put that in first because I don't want to accidentally cross that asymptote. That is a huge no-no. And then just take some of your points and move them 3 to the right and 2 up. Asymptote we said was at x equals 3, right? What's our y-intercept for this?
looks like 0.
Kind of looks like 0. Are we sure it's 0? Did we move something and actually have it land at that spot? So we're going to have to put 0 in this one. Now, this is another one of those nasty ones where things are not working out nice. We're actually going to have to put 0 in and see what do we get. So go back up here. Can we just put the 0 in? Oh, for finding it? Well, on the test, we're probably going to have a nice one anyway, you know. But yeah, you should try and find a spot to show the work if we're going to put the 0 in there. I don't know if you guys have any available at this point. These are pretty tiny. Well, let's put a 0 in. Show all the steps here. So we will have 2 plus, using the change of base formula, logarithm of 3 over logarithm of 1/2 or 0.5. And then we'll add 2. So that's where it was supposed to be. 0, approximately 4.15. But it's a logarithm, so let's go with 0.4150 and do the 4 decimal places, like logarithms are supposed to be done. Oh, I'm going to use a different color because that's not going to show up. Unless it lands perfectly on the 0, 0, we have to plug it into the calculator just to see where it's going to go. Domain? Negative infinity to 3. Range? Everything? Do we have both end behaviors? No. Which one do we have this time? Negative infinity. So limit as x approaches negative infinity.
Infinitum.
Is this an f of x?
No, GLS.
Let me rewrite it. It's getting so small here. Wait. G of x equals, did you already say it? Where are we going
Yeah.
forever? Ooh, there's a lot of work for that problem. Good stuff though. You know, we can get all that in the shape, and then all we're doing is counting to translate that. Now, again, remember, vertical stretches, reflections have to come before translations. Horizontal stretches and reflections have to come before horizontal translations. But the order is up to you. As long as you follow those 2 rules, there's a lot of ways that we can make this happen. So now, let's just focus on a piece of that instead of the whole, let's do the whole whopper here. Finding the domain of some that are a little weird, some that don't fit our A, H, and K stuff. But we've done a couple of these now. How do we find the domain of this? I mean, what are we interested in here? What's the big deal? The domain is the x's. What are we putting in there? And it has to come out to be what? Greater than 0. We talked about this before. We'll add the 16 to both sides. We'll take the square root, but things get a little weird because we really should put the absolute value because it was something squared. But in the end, we need to think of that as a plus or minus 4. Now, here's the part you have to remember. We're just focusing on this, not the rest of it. We just want to know when is x squared minus 16 going to be greater than 0. And this we should be able to graph in our head. Because this is a parabola. And where's its vertex? 0, negative 16. So in our head, we should say, okay, this is starting to make sense because they're telling me it has to be here and here. Because that's where it's going to be greater than 0. So, how do we write that? Negative infinity to negative 4. 4 to, that doesn't look like a 4. There it is. So the visual, again, is a huge help. Whether or not you have to make the sketch or not, just kind of use that visual to get everything where it needs to be. So there's a lot of blah, blah, blah in B. What's the only part of that we're interested in? 4 minus the square root of x. That's what we're interested in. We want to know where is that going to be greater than 0. So a couple ways to do it. You could add the square root of x to both sides. That way you're not going to have to divide by a negative if you didn't want to. And then we'd have to square it, realizing, of course, that every once in a while produces an extraneous solution. So if I turn this around, it's going to say x is less than 16. But there's another something going on here because we have a square root up here. In order to graph it, what do we know about the x values that go under the square root? Could it be 0? Could we put 0 in here?
Yeah.
That's okay. So we're going to need stuff between 0 and 16. So, 16 to 0? If we put 0 in here, we're okay?
Yeah.
Where's that going to start us at? So the logarithm of 4. So could we put 4 in here? If we put 4 in here, what would happen?
It would not be a good situation.
It would be a 2. So it's like, okay, well, how do we know where to do this? Do the visual, graph it, take a peek at it, and see. Just the 4 minus the square root of x.
Let's go with 20.
Why aren't we seeing it cross below the x-axis? Where did we say it was going to cross?
16.
16. So maybe we want to make our window bigger. Maybe we want to go in here and change this so that it's like 20, so we can see it. There it is. So from 0 to 16, we were right, but here's what I want everybody to remember. We have to know whether or not we can use exactly these numbers. So if you put a 16 in there, is it going to be greater than 0? It's crossing at that point. Can we put a 0 in there? Yes, we can. It's going to work. So that one needs a nice little set of square brackets. That doesn't look exactly square down there. So we can use that piece. But the visual, putting that together, for some reason, I don't think maybe in Algebra 2, square root of x, graphing that gets covered enough, because most people aren't real comfortable doing that one in their head, but parabolas, absolutely. Thanks.
So if it crosses it, it's not as quick back.
Because it would be equal to 0.
It stops right on it.
Yes, because we can put a 0 in here. That's what we're saying. If we couldn't take the square root of x, then we couldn't include it. So square root of 0, we can do it. We can include it and actually have it in there. All right. This next piece is really calculator heavy. So grab your graphing calculator while I hand this up. Oh, wait a minute. This was already moved anyway. Dun, dun, dun. When seeking a blank for a set of data, we're always looking for models. Always looking for a model for a set of data. Often helpful to transform the data by applying a function to one or both of the variables in the data set. We didn't talk about it as a transformation, but we have already done this. When we say, you know what, let's use a 0 here. I don't want to punch all that stuff in. That's actually a transformation. So instead of using 1900 to 2000, we said, no, let's just use 0 to 1000 or 100, so we're not punching all that in. Such a transformation of a data set is called a re-expression of the data. Now here's the deal. I had mentioned this before. There are lots of numbers that we deal with, especially when you're talking about space, that are really huge. And they get to the point where your calculators can't handle them well, your computers take a long time to calculate them. So what we generally do is say, let's re-express these with logarithms, because logarithms will make them something we can handle, a number that we could work with more easily. So this says, astronomically speaking, an astronomical unit, an AU, is the average distance between the Earth and the Sun, which is about 149.6 million kilometers. And that gives us all these lovely numbers here. But now we say those are huge numbers to begin with. And this stuff was all about the Earth and the Sun. Well, these are different planets, so your perspective changes when you're on a different planet. What we would want to do is change all of this data so it's talking about Earth stuff. What's an Earth astronomical unit? And the days of an orbit on the other planets, that doesn't match ours. So if we want to talk about this intelligently, we would need to change all this information so it had to do with Earth, because that's what we know. So recall from section 2.2 that Kepler's third law states that the square of the orbit period t for each planet is proportional to the cube of the average distance a from the Sun. Those two things are going to be proportional to each other. It says if we re-express the Kepler planetary data from that table, it becomes more workable, easier for us to use. So what they did was they went ahead and divided all of this information according to Earth. So this was all divided by astronomical unit box up there. It's so tiny, 149.6. So all of this data was divided by 149.6. Now, just looking at that column, everybody, what just happened that was really good about that? Earth is 1, and they're small numbers. So Earth is how we put our perspective. That's the only planet we've ever lived on. That's what we know. And then the period of the orbit back here, well, we do that according to Earth days. And in fact, let's see, they divided by 365.2. So they did use the perfect year.
Wait, what's the point two? What's that? Oh, yeah.
So why the 0.2? Leap year. Remember, leap year was built in because 365 is not perfect. It's not perfect. It's a little off. So 365.2 puts that in terms of days on Earth. So here's what they want us to do. They want us to see that the graph of the original is going to be almost the exact same as the graph of the data that's been done with the natural log. So we are going to go ahead and put this stuff in. So grab your calculator. And yeah, I'm not going to record from the smartboard or it's going to really take forever for me here. So second, actually, oh gosh. Yeah, I'm going to cheat. I already put this in yesterday so I can go through it with you a little faster today. So there's not a lot of data. Go ahead and put them in. List 1, list 2. Did you put both tables in your notes or just the one?
Yeah,
Just the one. Okay. That's because we needed to make it bigger. I remember if we put both tables in, it was so small you could barely see those numbers. But we took the other table out because it's in your book. Just get it out. Once everybody has them in, we're going to re-express these with natural logarithms. Anybody need more time to punch? Here's how we're going to do it. We're going to go to list 3 way up at the top, and we're going to tell it, take the natural logarithm of this stuff. So we're going to do ln of list 1, so second number 1, parentheses. That tells it, take all of those numbers that we have there in list 1 and give me all the natural logarithms. Boom. Touch a button that does that. But now we also have to re-express the y's, which is the list 2. So we're going to go to list 4 and do the same thing. Natural log. Second, list 2, parentheses. That way we're putting all of this data in as natural logarithms. So we've got a new set of numbers. Under stats, edit, you just go up to the name and hit ln and then tell it which list you want it to do that for. So second 1 is list 1, second 2 is list 2. Now the natural logarithms are expressed in list 3 and list 4. Alrighty. Now, I'm not going to make the scatter plots up there. You can see them right here. Here's what they're saying. If we graphed the original data and we graphed those natural logarithms that we just put in list 3 and list 4, look at how similar that graph is. You really haven't changed how the scatter plot looks, which means you're not changing anything as far as regression goes either when you do that. So it says, notice that the pattern in the scatter plot of the re-expressed data is essentially the same as the pattern in the plot of the original data. What we've done is just make the numerical values of the data more convenient. That's what we're doing. And to guarantee that our plot contains the ordered pair 1, 1 for Earth, which could potentially simplify the model. Obviously, having a 1 for your frame of reference would be really, really nice. What we have not done and still wish to do is clarify the relationship between the variables A, the distance from the sun, and T, the orbit period. So that's what's left to do. So here's what we're going to do. We are going to re-express the data to arrive at Kepler's third law. On the next page. Re-express the data pairs as natural log and natural log. We just did that. That's our list 3 and our list 4. Now find a linear regression model for those two pairs. Okay, well that just means we need to do a linear regression with list 3 and list 4. So let's do that. Stats, calculate. Linear regression, but I have to tell it this time I want list 3 and list 4. We don't need to store this one. I was just thinking whether or not we should do y variables. We don't need to store this one. So after you change it to list 3 and list 4, you can go all the way down to calculate. So what I'm going to do is try to show you that you do know the math to arrive at Kepler's third law. All right, we have this so far. And I look at it and I think 0.0007. Statistically important.
Where'd you get that? Where'd you get the point?
This was linear regression from list 3 and list 4. Oh, look at me. See, it's times 10 to the negative 4th over there. So, yeah, you got to move the decimal over. Sorry, I forgot to mention it. This is not going to be statistically significant. So really what we have here is that. Now, let's take it a step further. 1.499. That's really close to something much nicer, right?
1.498.
I hate the burning passion.
Where'd you get the 0.007?
Oh,
If you look at the calculator,
take a peek.
e to the negative
Look at
fourth.
the calculator.
And most people, we're not going to because we're trained to look for those 3 decimal places. But when you look over here, it's telling us with scientific notation that's times 10 to the negative 4th. That means we have to move the decimal over 4 places to the left. And that's what gives us really teeny numbers, is scientific notation with negatives. So that's really, really teeny number. In fact, like I said, it's not statistically significant. 1.5, that's a fraction, isn't it? How do you write that? 3 halves. Now, remember, we re-expressed this data. So what we're really doing right now is the natural log of A for our x's, and for our y's, the natural log of t. That was what we re-expressed the data as. We put them in there as natural logs. Well, I'd rather just have the number on one side. I think I'll go ahead and divide by natural log of A on both sides. Hey, isn't this what we get when we do change the base formula over here?
Sure.
So wouldn't this really be logarithm base A of t?
If you feel that's what it is.
Well, think backwards. If you snail shell this, well, actually snail shelling for the logarithm, we just need this piece, which is logarithm of what you're trying to evaluate over logarithm of base. So we're using change of base backwards. Now, let's snail shell that so we don't have any logarithms. With a to the 3 halves equals t. I get a feeling we're really, really close, because remember, what we're trying to get is
What am I
this.
supposed to do?
we're supposed to get this. That's Kepler's third law. I think we're really, really close. What do we need to do to both sides of this to get Kepler's third law?
Ew.
That's where Kepler's third law came from. Bless you. That's where it came from. We re-express the data, bless you, and notice here this happens. All right. So, are you going to have to do that again? Absolutely not. We're not going to have you recreate that on your own, but you need to know that formulas come from someplace. You know, there's math for this. Now, believe it or not, somebody came up with a formula about how long we retain information in our brain. This is Ebbinghaus's law of forgetting. It states that if a task is learned at a performance level P of 0, which means when they tested you, you got what percent on it, then after a time interval T, the performance level P satisfies this logarithm equation, and that's because we forget stuff, you know? Stuff that normally was in our long-term memory gets replaced with other long-term memory. So where C is a constant that depends on the type of task, and T is measured in months. Now what that means is they're going to have to tell us C. They've got a little book of Ebbinghaus's law of forgetting constants somewhere, and we're going to have to use that. They'll have to give us that. But we want to know, how long does it take before you start forgetting stuff? Or 3 months later, how much are you going to remember? So what they want us to do is solve this big mess for P. So I start thinking, well, that means we've got to condense it, because this needs to be 1 logarithm equals 1 logarithm here. So let's see. This C came from up here. And what did subtraction do? Divide. So it was log of P sub 0 over, and I don't need the other log, I just need the T plus 1 to the C. You see how they both have the same logarithm? So that's not what makes this equal. What makes it equal is that P has to equal P sub naught over T plus 1 to the C. So we actually could drop the 2 logarithms, or, so it makes a little bit more mathematical sense to you, you could do this. You could exponentiate both sides. And you could say, I'm going to take 10 and I'm going to raise it to this. Well, this is logarithm base 10. That's going to drop out. I'm going to take 10 and I'm going to raise it to this. This is going to drop out. There's your solvent for P. There it is. So that's the formula that we would get. Now, B has us actually use this. It says, you scored a 90 on a math test. If you took the same test 2 months later, what could you expect your score to be? Well, you scored 90. That was your initial P. I guess we could think of that as just some kind of score. It said performance level, but we're performing at 90%. Down on the bottom here, the time is going to be 2 months. It said this formula is measured in months. So we're just going to put 2 right here. And remember, they had to give us C because it's specialized for this formula. So it says, assume that C is 0.2. So go ahead and crank that out for me. What's your new score going to be after 2 months of not doing this? Instead of 90, oh, what will you get?
Tears.
Tears.
Okay.
72.
72? So after 2 months of not working with the stuff, you're going to get about a 72.47.
What's the point of a final then?
To force you to remember that information.
That's angry.
After a year, you haven't really looked at it. You had a 90 on that first test.
No.
What do we put in for months? 12. Still going to use that little 0.2. If we gave you the exact same test a year later, give me the score that you could expect with Ebbinghaus's law.
I had a question.
Oh, that's part of the formula from the T+1 up here, Matt. Yeah, that was part of Ebbinghouse's formula. What's the bad news, everybody?
Going to fail.
0.883.
This law matches the statement, if you don't use it, you lose it. I mean, that's what it is. But you need to know the formulas come from somewhere. That's why I really wanted to go through that Kepler's third law derivation for you, so you know, they don't just make these up out of thin air. They do see patterns, and they use those patterns to give us what we need. So, oh, I'm running short, aren't I?
I probably do.
And some of the problems that we went through in the book, like I told you, we're not gonna have you recreate. So typically, especially with this assignment, what we did in class is more difficult than what you see here. So don't get worried that you're gonna have to derive a bunch of physics laws or anything. We just wanna make sure that you understand they came from somewhere and somebody did some math to get them. They didn't just look them up on the internet and say, hey, this looks good, let's use it. There's
Are you
math
sure?
behind it.
That's pretty good. That's pretty cool.